start with at least telling something about Karthik. So finally, I mean, if I understand, Karthik, you were doing computational geometry, right, in your master's avatar?
Right, and chemistry before that.
Exactly. So it's very fabulous journey from chemistry to computational geometry. Then you went to Israel and you did hardness of approximation, largely.
Right.
Okay, and then you went to US, and this love for hardness of approximation continues. So if I have to ask you what you like, making algorithms more or making hardness reductions more? This is my favorite questions to all the people who make such things.
I see. I personally like to find out the truth, and I feel better equipped to do hardness of approximation.
Okay. So given that, now that he feels much more equipped, so we will know what all equipments he uses to prove this hardness of approximation. So yesterday, Karthik gave us a very nice overview of the kind of things which have been being done in clustering and where the field is. And today, he will delve deep into some of these tools and techniques and tell us how new generation of hardness of approximation in metric clusterings are being done. So Karthik, over to you.
Thank you, Saket. So today I want to start with some slightly philosophical overview, which is I want to sort of put all the problems that we study, which are NP hard, into some kind of perspective based on the notion of approximation. And this is very, very philosophical, so it's hard to formalize it, but let me try. So I want to put things on the spectrum of structure, where on the least structure end, we have circuit SAT and CSPs of large arity, where it's very easy to prove that they're very hard. And even hardness of approximation, even very hard to approximate. And then one of the remarkable results in TCS over the last 40, 50 years is this Pcp theorem, which says that, it's not just any arbitrary CSP, but CSPs of constant arity are still hard to approximate. So you have a little more structure. And then we were able to prove these hardness approximation results for not just some label cover, some abstract formulation, but like concrete problems like set cover, set systems, natural computational problems that arise from set systems. We are able to prove strong and tight hardness of approximation results. And then what next? We wanted locality. So what about 3-SAT or 3-LIN? We were able to prove tight hardness of approximation results. And at each time, there was a new set of techniques that were needed. Like for set cover, we needed the parallel repetition theorem. For 3-SAT and these things, Fourier analysis came in. So each time when we needed more structure and we wanted to prove hardness for more structured problems, we had to bring in more tools. And then after that, we looked at graph problems. And here we have a tight understanding, assuming the unique games conjecture. And again, we had to bring in a lot more Fourier analysis and a lot more tools into this thing. But then here sits this set of geometric problems whose understanding from hardness of approximation was very, very bad. All we were able to say is that, okay, there is no PTAS. But the approximation community is like intensively working on it from an algorithmic point of view. So there is this disparity, and as there is more structure, it becomes hard to prove hardness results. And somehow, so we needed tools to understand this. And while the unique games conjecture sort of addressed all the graph problems that we are interested in, giving us tight understanding, there was nothing really to capture these geometric problems. And in particular, like yesterday, I told about clustering. And so there was this need to put forth this Johnson coverage hypothesis. The idea being it's this intermediate problem with very little structure. It's just some set system problem. And yet it implies all these tight results for clustering. So, okay, then we have reduced the problem to proving hardness of something that has less structure, which is always an easier thing to do. And the nice thing is that a weak version of the Johnson coverage hypothesis is just the vertex coverage problem, whose tight understanding we know from the unique games conjecture. So it's not like completely baseless. We at least get something out of it. Okay. So I'm going to, now that we have the perspective right, I want to show how the Johnson coverage hypothesis implies these tight results for clustering. But before I do that, yesterday I promised I wanted to show how to embed things for the K-center problem. And that sort of sets up the techniques that we need for the Johnson coverage hypothesis. So we will revisit the K-center problem, where things were more or less known in the 80s. Here, the input is a point set X, which we want to cluster, and a set of candidate centers S. And we want to sort of identify K points in our set of candidate centers such that the radius to every point is minimized. So if you look at any point X and you cut its closest center, and you want to minimize this distance over all points X. Okay, so we have the K-center problem. And what was known in the general metric, we knew that there is a simple 3 approximation algorithm and that is tight. And we had seen the proof. It was from the max coverage problem, where if the sets correspond to centers and the universe elements correspond to the points that we want to cluster. And in the yes case, there are K sets or K centers, which are all covering it. So it's a distance 1. And in the no case, if there are any K sets we pick, one of the universe elements will not be covered, so you'll be paying distance 3. So that's how we get this result. But now let's try to show things so we get this 3 in approximability result in general metric. I want to show the same, but now for the L1 metric. So let me try to show how the embedding is done. And I will also make a few comments about how things are done in the Euclidean metric and so on. So all these things for L1, L infinity Euclidean are known in the plane, so in dimension 2. But today I'm going to show it for n dimensions. And what we need is a special case of the max coverage problem, which is the vertex coverage problem, where you're given a graph and an integer k, and your goal is to cover as many edges as possible using k vertices. When I say cover, it means that the edge is incident on, the vertex is incident on the edge. And we know from the results by Karp that this is NP complete to determine if there are k vertices that cover all the edges versus k vertices, any k vertices miss at least one edge. And how do we do this embedding? Well, we're going to do it in Rn. So such that if there is a vertex coverage, then the K-center cost is going to be 1. And if there is no vertex coverage, that means that every K vertices miss at least one edge, then we are going to show that the K-center cost is at least 3 in the L1 metric. Let me make this point already that this is in Rn, but you can also do it in R2, and I will tell how later. The idea is very simple. You think of the bipartite graph between the edges and the vertices. And you think of this as all subsets of size 1 and all subsets of size 2. And when you think of things as subsets, there's a natural way to think of them as points in 0, 1 to the n, where you look at the characteristic vector, where if an element belongs to the set, then you put a 1, otherwise you put a 0 on that coordinate. And now when we do this, it happens that if a vertex was hitting an edge, then their distance is going to be 1. And if a vertex was not hitting an edge, then their distance is going to be 3, just because the cardinality is 2 on top and 1 on below, and there is no matching happening. So just because of this, we have that if we took the bottom as our candidate centers and the top as the points to cluster, and we are in the L1 metric. So we have, naturally, we get that the 3 in approximability continues here as well, because in the yes case, everything is going to be at distance 1. And in the no case, any k guys we pick, any k vertices we pick, there's an edge that's not covered, that's going to be at distance 3. And of course, this is in n dimensions. And so we get this result. And this also gives a gap of 1 versus square root 3 for Euclidean metric, because you have to take a square root. Now, how do you get those tight results for the previous case? Well, you start with planar vertex cover of degree 3. And we know that this is still NP hard. And then you're in the plane, and then you can look at some more specialized embeddings, which give you this distance, because you can always subdivide edges and the hardness continues to hold, and you just make sure everything is like a line. Okay. But the reason I presented this proof is it's going to be helpful when we are looking at the Johnson coverage hypothesis. And for the Euclidean metric, there's more careful analysis of geometric objects that one has to do, but let's skip that for now. Okay, now that we got a flavor for K-center and what kind of embeddings entail, let's go back to our K-means and K-median. Again, here the objective that we want to minimize is sum of distance squared to the closest center for K-means and sum of distance for K-median. Okay. And what we saw yesterday was that, in fact, in the general metric, it's 3.94 for K-means, and that's tight even for L1 or L infinity metrics, assuming the Johnson coverage hypothesis, and you get some strong inapproximability results. I'm going to deal with the discrete case first and then the continuous case. Recall that for the general metrics, you just looked at the set system and 1 and 3, and this gives you, we had the hardness of approximation for max coverage, which was 1 minus 1 over E factor. So in the yes case, you pay 1 everywhere, and in the no case, for 1 minus 1 over E fraction, you pay 1, and for the rest, you pay 3. And if it's K means, it's like 9 because it's distance square. So you get 1 plus 8 over E. Good. Cost is 1, cost is 3, and we are good. So we get this 1 plus 8 over E result for the general metric. Now, let me again recall what the Johnson coverage hypothesis is. You're given as input subsets of size T over a universe of size N, and you want to identify K subsets of size T minus 1, such that every subset, in the yes case, every subset of size T contains one of these K subsets of size T minus 1. And in the no case, a uniformly random subset. So once we fix the any K subsets, a uniformly random subset in our input of size T is not going to cover any of the K subsets that we picked with probability 1 minus alpha. And this becomes, and if T is 2, this is essentially the vertex coverage problem. Because you want to pick vertices as your solution to cover edges. And the hypothesis says that as T increases, the ratio tends towards 1 minus 1 over E, the inapproximability. Okay. And I'm going to just make this clearer with a picture. But let me state the theorem first that I want to show the proof for. So assuming the alpha T Johnson coverage problem that, when at the Tth layer of the Johnson coverage problem, it's hard to approximate to a factor alpha. From that, we are going to construct an input for clustering in the Hamming metric, where we are in log n dimensional space, and we want to construct 2 point sets, such that in the yes case, the cost is going to be n prime. And in the no case, it's going to be 1 plus 8 times 1 minus alpha times n prime. The intuition being, in the yes case, you're going to pick those K sets of size T minus 1, and each one is going to be at distance 1. And in the no case, any K sets of T minus 1 we pick, alpha fraction of them is going to be at distance 1, and the remaining 1 minus alpha fraction of them is going to be at distance 3. And because you're taking square, it's 9. So it's going to be alpha plus 9 times 1 minus alpha, and then you get 1 plus 8 times 1 minus alpha. Okay, good. So, and then what happens is that if we plug in our hypothesis that this is hard to approximate to a factor 1 minus 1 over E, here you get 1 plus 8 over E, and you're in the Hamming metric. So this also extends to the L1 metric. So you get all these tight results. And instead, if we plug in 0.932, which we know already from the unique games conjecture for the layer 2 for vertex coverage problem, here you get the value 1.56. So these are just plugging in the known hardness results. So what's the intuition? The idea is you look at this bipartite graph again, where you have all T subsets on the top and all T-1 size subsets at the bottom. So our input is going to be all the things at the top, right? Like, because we're going to get a subset, we're going to get a collection of subsets of size T. And our goal is to find K guys in the bottom, T-1. And we think of these as points in 0, 1 to the n by looking at the characteristic vector. So all the things on the top are going to have T many ones, and all the things at the bottom are going to have T-1 many ones. And I'm going to refer to this as the Hamming weight. So everything at the top is going to be of Hamming weight T, and everything in the bottom is going to be of Hamming weight T-1. And the nice thing is that if a set of T-1 is contained in a set of size T, and then you look at their vector characteristic vectors, they're going to be at distance 1 in the Hamming metric or the L1 metric. Whereas if you take two sets, one in Hamming weight T and the other in Hamming weight T-1, and one does not contain the other, then they're going to be at distance 3 away. So this is where you get the gap between T and T-1. But the point is we are in n dimensions. So we need to somehow go from n to log n. And we don't have the Johnson-Lindenstrass theorem or any of those dimensionality reduction tools here. So what do? We design a communication game. Okay. So we have two players, Alice and Bob. And Alice has a subset of 0, 1, 1, 2, 3 up to n of size T. And Bob has a subset of size T-1. So we're thinking of a communication game where Alice holds a subset of size T and Bob holds a subset of size T-1. Good. And this is a one-way communication game. So both these players get their inputs and Bob will send some messages to Alice. Okay, so this is the code. And they both have access to public randomness. So they both can jointly toss some random coins and know the outcome of these random coins. What is the goal? The goal is for Bob and Alice to know if Bob's input is contained in Alice's input. So Bob has a set of size T-1, Alice has a set of size T. They have to somehow decide if Bob's set is contained in Alice's set, and they have some public randomness to do this, but only Bob can send one message to Alice. Okay, so this is the game. This is the containment game. And of course, Bob can just look at every element in his set and just send all those elements as they are. So each element can be encoded using log n bits, and there are T many elements or T-1 and many elements. And Bob can just send all of those. So he can just send the entire input to Alice, and Alice is just going to then check if Bob's set is contained within hers or not. And you have completeness 1 and soundness 0 in the sense that if Bob's set is contained, then Alice will know for sure that it's contained. And if Bob's set is not contained in Alice's set, then Alice will for sure know it's not contained. So you have like perfect thing. But the problem is the message length is too much. I don't want to send T log n bits. So what we're going to see now is a randomized protocol where you send a constant number of bits, where the constant only depends on T and some error parameter epsilon. So independent of n, that's the important thing. And this will have completeness 1 in the sense that so the idea is the following. Alice and Bob both get their inputs. Let me go back here. Alice and Bob both get their inputs. Both of them toss some random coins. And then Bob looks at the input and the random coins and is going to send a constant number of bits independent of n to Alice. Alice then, on receiving Bob's message, is going to look at the randomness, her input, and the message Bob sent, and decide to whether accept or reject. Now, what we want is that Alice always accepts if the set S is contained in T, and Alice rejects with very high probability otherwise.
So, Karthik, just to make it clear, when you say public randomness, so suppose they both decide on what you call tossing a coin together, or if anybody tosses a coin from here, other can know the outcome.
So both ways are fine, in the sense that both of them jointly toss a coin together and they see the outcome of that randomness, or someone else tosses and they both know the same outcome of the randomness. The main point being they agree on the random bits. Okay. And so here we can make epsilon as small as we want, any small constant as we want, and we are just sending constant number of bits. And in the yes case, if the set is indeed contained, Alice always accepts. And in the no case, she will accept with probability just epsilon. Okay, so we're going to see this protocol. And once I show the protocol, the next thing to see is how this protocol will be used to reduce the dimension of our clustering instances. Okay, so in order to show this protocol, I need an error correcting code. So let Q be some large prime, and we can encode our universe, each universe element in FQ to the log n. Of course, we can do it in F2 to the log n, so we can definitely do it in FQ to the log n. So an error correcting code is just some function which is going to take log n field elements and output C times log n field elements for some large constant C. And the idea is that even if the initial two strings differed on only one coordinate out of the log n coordinates, in the output, when you have the C log n bit strings, C log n field elements, they're going to disagree on most locations. So that is what an error correcting code is. And so let's take an error correcting code. And what Alice and Bob do is first uniformly toss some random coins and agree on a coordinate of the encoding. So they're going to just jointly toss some random coins and agree on some coordinate of the encoding. And then they're going to encode their own sets. So what they do is Bob first encodes. So Bob has T-1 universe elements. So, and each element Bob independently encodes it and then looks at the ith coordinate and sends the ith coordinate of all the T-1 universe elements encoding to Alice. So Bob has, say, U1, U2, U3 up to UT-1. Then he's going to encode each one of them. So he's going to encode C of U1, C of U2, C of U3 up to C of UT-1. Look at the ith coordinate of all these encodings, and then just send the ith coordinate. Okay. Then Alice herself has T universe elements. She will encode all of them and look at the ith coordinate and create the set Ti, which is the ith coordinate of all the universe elements encoding she has, and check if the message that Bob sent is contained in the message that in her own Ti. And if it is, she accepts. If not, she rejects. Okay. So let's look.
Something, Karthik, I did not understand. How does Alice checks whether SI is like
so
Bob set is contained or not? Okay.
Right. Bob will send SI. Bob has a set S, but he's not going to send S because S requires too many this. So what he does instead is he encodes S and then looks at a specific coordinate and only sends that.
Yes. And then what does Alice do on those after getting those coordinates?
Right. So Alice knows the coordinate I and knows basically some field elements. So Alice has received some set. So Alice herself will compute the set Ti based on her input. and check if the set she received is contained in the set Ti.
Okay.
If yes, she accepts. If no, she rejects.
Okay, thanks.
And the key point here being Bob's message is not T minus 1 times log n, but T minus 1 times log q, where q is just some large prime, which we'll pick to be some large constant. And the soundness of this protocol, which we will see, is that it is T times 1 minus the distance of the code. Because any two code words can agree on at most 1 minus delta C locations, the distance of the thing, and there are T things that in which they can agree on. So we're going to see that it's at most T times 1 minus delta of C. Okay. So this is the protocol, and this is the claims. And now the point being that if we choose algebraic geometric codes, and only with algebraic geometric codes, this value becomes 1 over square root q. So you can just choose q to be any large prime that we want. And in the yes case, Alice always accepts. And in the no case, she accepts with probability 1 over square root q, which tends to 0 as q becomes large. Okay. So now now that I described this protocol and these claims, I want to describe how this is used to create the embedding. So we are going to embed every subset to be a vector in 0, 1 to the q times c times log n. Notice that c is some large constant, q is some large constant. So we are really in O of 1 log n, O of log n dimensions. And so every subset, we're going to create a vector in O of log n dimensions. Okay. And in order to define this embedding, let me first fix an I in C log n and a subset S in of some cardinality in the universe 0 in 1 to n. So we have fixed a set in the universe 1 to n, and we have fixed a coordinate I. So notice that that means that I have to define, if I can define q bits, then I have defined this thing, because what I have to define now is tau of s on the block I. So I really think of tau as embedding into C log n many blocks, each block containing q bits. Now I have fixed a block I, and I have fixed my input s. So I just have to define what these q bits are on the ith block for s. And this is just going to be, you're going to look at the subset S that will contain certain elements. And then we are just going to look at the encoding of those elements on the ith coordinate. So you get basically some field elements. Okay. So again, let me repeat. So you have some subset S of the universe 1 to n. Then we encode it using our function, error correcting code function C that we had. And once we encode it, then we look at the ith coordinate. Now, if the cardinality of S was T, then on the ith coordinate, we're going to see T field elements. And now these T field elements, so now we have to write it. We are going to write it think of it as a subset of Q, these T field elements, and we're going to write the characteristic vector. So on the ith block, we are going to write the characteristic vector of ESI, where SI is the ith coordinate of the encoding. Okay. And let's give an example. I'll give a couple of examples. So consider the set S, which is 1, 2, 3 up to T. And now let's look at S1. Of course, the first coordinate of the encoding, it's just the same, 1, 2, 2 up to T.
So Karthik, I have a question. I mean, I want to understand what you're doing in this slide with respect to what you described in the previous slide.
Okay, so the previous slide, I described a randomized protocol for this game that I created.
That is over assuming the black box of that code, correct?
Right. There is some error correcting code which you can take black box from the shelf that is known in literature.
Right. So, and you're not going to prove that probability thing. That's also assumed, all right? That
I can.
no, okay.
I can do it, but let me do it in the soundness when I actually need it.
Sure. Now I've just, so what is it now you are doing?
I'm going to show how we can, I'm going to construct an embedding of the protocol we saw and see how we get points in space.
Okay. Okay.
So I'm going to embed every subset as a point in space. So then such that certain distance properties hold. And then I'm going to put all of them together to do the reduction to clustering from Johnson coverage hypothesis.
Thanks. Yeah.
Okay. So let me just confirm what the embedding does here. So suppose we had the set 1, 2, 3 up to t of universe size n. And let's look at its encoding. And let's suppose on the first coordinate, they're exactly what they are, 1, 2, 3 up to t. So then on the first block, you would write 1, 1, 1, 1 t times, and then all zeros. So you have a block of size q bits, which contain the first t coordinates are 1, and then the rest are zeros. So that's what is here. But suppose let's look at some ith coordinate of, and then on the ith block, you have that the field elements are 1, 2, 3 up to t over 2, and then q minus t over 2 plus 1, so on up to q. So you have like ones in the top and ones in the bottom. So then on that block, you write the first t over 2 ones, and then all zeros, and then t over 2 at the bottom. So this is how the encoding would look. You're going to take a subset, and for every subset, you have a large number of coordinates divided into blocks. There are C log n many blocks. Each block is of size q. And in q, you write the characteristic vector of their encoding on the ith coordinate. Okay, so this is the embedding. And of course, now we can define a reduction, which is you are given as input the Johnson coverage hypothesis instance, which are subsets of layer T. So you have a collection of subsets of size T. And from that, we are going to create a point set, which is just all the you take the subset and embed it using this function tau. And so you get this collection of points, and these are the points that we want to cluster. And the set of candidate centers are going to be the embedding of the entire layer T minus 1. So you look at every subset of size T minus 1, and then you look at its embedding under tau, and that is the set of candidate centers. And the claim is, of course, that in the yes case, if there were k subsets of T minus 1 that covered all of your subsets of size T, then here they will have that after doing this embedding, if you look at the points, corresponding points, then those k points of Hamming weight, whatever they are going to be at distance 1. So for every point in X, you're going to have one of these k points, which is at distance 1. So we are going to see this claim with more pictures. And before I do that, let me make a couple of structural observations that become very handy to convince why this proof goes through. Suppose we have two sets, S and T, and S is indeed contained in T. Then you look at any block I, we have that Si is contained in Ti. Why is this the case? So what is Si? Si is just the encoding of all the elements in S, and you're looking at the ith coordinate. Now, all the elements in S are also in T. So if you look at Ti, you're going to look at all the elements that are there in S and maybe more. And then you're going to look at the ith coordinate of their encoding. And since you're just taking unions and you're just including things, Si will definitely be contained in Ti, because Ti is just contains Si and something else. And now if this is the case, then if you look at the qth block, if you look at the ith block, and you'll have basically two characteristic vectors where of sets one containing the other. So it will be that all the places where SI is 1, TI will also be 1. But on top of that, if say TI contains one additional element, then it's going to have one more in one other place. So their distance is going to be 1. Because wherever SI is 1, TI is 1. Wherever SI is 0, in at most one location, TI can be 1 other location. And everywhere else, it's also 0. So on that specific location that where the additional element is, there it's going to be a distance 1. Okay. So the bottom line is that if S is contained in T and F is of cardinality T minus 1 and T is of cardinality T, then for every block I, we have that SI is contained in TI, and moreover, we have that the distance of after you embed them using tau is going to be at 1. Okay. But what happens if S is not contained in T? Right? Then the claim is that for most blocks I, we have that SI is not contained in TI. This follows from the encoding property. But let me try to first say about the embedding. That suppose you had, you looked at everything here SI minus TI, and it contains at least one element, right? So there is one place where you write 1 in SI, where you write 0 in TI. And by definition, since TI has one more element, there will be at least 2 elements in TI where you write 1 and you write 0 in SI. So their distance will be at least 3 on that block. And for every block in which SI is not contained in TI, their distance is at least 3. And this is true for most blocks. So if you look at the embedding, it's going to be almost 3 overall because you average over all blocks. Okay. So let's complete the reduction now. So in the yes case, there are these K subsets of size T minus 1 that cover all of E. And then we are going to just build the natural embedding where you look at the embedding of these K subsets, and then we just map it to the closest center, each one. So you look at any set T, which you want to, and so the point corresponding to set T, and that just maps to the SI that covers it. And because of this property of tau, that it's going to be a distance 1 on each block, we have that if you fix some T, and if you fix some block I, then the distance is going to be exactly 1. So let's look at the k-means objective. We have C log n many blocks, and on C log n many blocks, it's going to be a distance 1. So since we're looking at distance square, it's going to be C log n square times the number of points that we have. Because for every point, the distance to its closest center on each block is 1. And so for every point, the distance to its closest center is going to be C log n. And so the distance square is going to be C log n square. And this is true for every point. So it's times x. So this is the completeness. And in the soundness, let's take some classification, sigma. And we can construct a solution, a candidate solution from sigma to our Johnson coverage problem, where because you're picking, there is this one-to-one correspondence between subsets of size T minus 1 and our set of candidate centers, you just go back and pick those subsets, which were picked as your solution in sigma. And now we know that there is this subset E prime of E, which are not covered by S prime. And that is a large fraction. That's 1 minus alpha fraction. So let's pick some subset in which is not covered. And we know that for most blocks, their distance is going to be 3. Okay. And since this is true for most blocks, then we can just assume that tau of t and sigma of t, tau of t are almost 3 distance away once you normalize. So the k-means objective is that for all those subsets not in E prime, we are going to be at distance 1 on each block. So that gives you C log n square because it's distance square. And for every other thing, you're going to be almost 9. So it's like 9 minus little o of 1 times C log n square. And so this, you end up getting like 1 plus 8 log n, because the size of E prime is going to be 1 minus alpha. So you end up getting that because of this expression, size of x E prime is going to be 1 minus alpha, and size of this is alpha. So it's alpha plus 9 times 1 minus alpha. So you get 1 plus 8 times 1 minus alpha. Let me just go back and convince you about the soundness here. So the soundness is going to be t times 1 minus this. Why? Because Alice has t sets, and Alice has t elements, and Bob has t minus 1 elements, and these are not all contained. In other words, Bob has an element that Alice does not have. So when Bob encodes this element that Alice does not have, that encoding can agree with any of the encoding of the universe elements of Alice on at most the distance of the code, 1 minus the distance of the code locations. And since Alice has t elements, you just take a union bound and you get t times 1 minus the distance of the code. Is this fine?
Yeah.
So we have this properties, and the soundness goes through. And so what we were able to show is that assuming the alpha t Johnson coverage hypothesis, in the yes case, you have n prime, and in the no case, you have 1 plus 8 times 1 minus alpha. Of course, if you assume alpha to be 1 minus 1 over e, you get those tight bounds.
So I have one question, Karthik. Okay.
Mm-hmm.
So I understand the reduction. What I'm not able to understand, where the communication gain plays a role here. Like why did you not directly go to the, to the embedding thing directly? Is this something which I'm missing here?
So there are two answers to this. One is historical. So the idea came from these things called distributed PCPs, okay. Where they had some protocol and they wrote it as an embedding. And so it's easier to think of these things as some protocols, and then the embedding comes out more naturally. Because remember that I described way before here. So this embedding works, correct, but it's in n dimension.
Correct.
And one can interpret this embedding as just the deterministic protocol.
I see. Okay.
And so once you have, okay, I have a deterministic protocol in n dimensions. So can I reduce the message length? And once you notice that the message length corresponds to the dimension, then it's just about coming up with a randomized protocol. So there is this one-to-one. It's connected in a loose level, but it helps to think of these things.
Okay.
Sir, I have one question.
Yeah.
For the containment game that you were discussing as of now, so you shared one deterministic solution, a trivial deterministic solution. So is there any other deterministic solution to the problem?
I think one can show that it's information theoretically not possible. That you need to send at least t log n many bits.
Okay.
Just because, yeah, you don't know which the elements are, right? And you want completeness 1 and soundness 0.
But like
so,
most of the time I see that the information theoretic lower bounds are like not very tight in such kind of problems.
Right. So you would be able to show omega t log n, and based on how careful the analysis is, you can put a precise constant over there. But for this problem, it's very, very simple that you should be able to show, I think, at least t minus 5 log n or something like that.
Okay. Thank you.
Okay, so this, so what the proof outline I gave sort of shows the L1 metric here, because we were in the Hamming. And now I want to sort of comment and not go into any proof details of how we get the other results, because all I showed was for the L1 metric. Let me start with how to get it for every LP metric. So what we do is, of course, you can just try to revisit the embedding and do directly from L1 to LP, but you lose a lot. So instead, we look at each block. And in each block itself, it becomes a subset. So whatever we had as the Johnson graph on universe N, what we have done is sort of reduce the universe to size Q. And then we look at embeddings here on Q, because it gives us a crazy amount of runtime. And there we look at embeddings from the Johnson graph to LP metrics. And we just sort of merge it into the protocol that we have. So if we had an embedding of subsets to the Euclidean metric, such that in the yes case, if it's contained, it's at distance 1, and it's not contained, then it's as far away as possible. Then we look at such an embedding and embed it inside the protocol. And that's how we get the tight results for a Euclidean metric, for instance. Okay. And as I said, for the L infinity, we are able to get NP hardness, tight at 3.94 and 1.73 in log n dimensional. And we get NP hardness because we use properties of the hard instances of max coverage that were constructed by Feige. And these the properties that are there sort of allow us to do this, because Feige constructs hard instances of max coverage even when the sets are of constant cardinality. And we need those hard instances in order to prove that we have an embedding for L infinity. So that's how we get the L infinity results. And the trickiest part is really the continuous version, because notice that in the continuous version, we don't have a set of candidate centers. So if you think of it in terms of the Johnson coverage problem, we are given as input sets of size T, but we can pick our centers anywhere. It doesn't have to be in layer T minus 1. So what one has to then argue is that if you pick sets in any other layer, then you would not be optimal, or in other words, okay, you can pick some sets in other layers, but then I can find an other replacement set in layer T minus 1, which is sort of good, like close to optimal. And hence, I can reconstruct from an arbitrary solution, a solution of layer T minus 1. And then you can go back to your vertex cover or Johnson coverage problem that we had. So the challenge in the continuous version is because you're not encoding the vertices if you are starting from the vertex coverage or layer T minus 1 explicitly as candidate centers. So the centers can be anywhere, and somehow from the centers being anywhere, we have to decode back a solution for the Johnson coverage problem and then show that we haven't lost much. So that is technically challenging, but things go through in a natural way as we expect. So in some sense, to prove all these results, all these things come together, like these graph embeddings and this communication protocol for dimensionality reduction, and everything comes together in one place. And let me sort of conclude with a small discussion on the Johnson coverage hypothesis, what's known, and then a few open problems. So as I noted yesterday, it's for T equals to 2, this is just the vertex coverage problem, because you have given layer 2, which you can interpret as edges, and you want to find things in layer 1, which are vertices. And here we know that there's an SDP which achieves 0.9292 approximation, and that's tight. But let's look at even the max coverage problem. And one can interpret the max coverage problem itself as you're given as input subsets of layer T, and you want to find subsets of size 1 such that it's covering. And this, so instead of finding subsets of size T minus 1, if we settle for subsets of size 1, then this is exactly the max coverage. And this we know approaches 1 minus 1 over E as T increases. And moreover, if one wants to prove just some LP integrality gap for the Johnson coverage problem, you end up with this amazing question, which is determine the smallest collection of size T minus 1 size subsets that hit all T size subsets. And this is the hypergraph Turan number, and it's been open since the 1940s.
So what's your definition of hitting? It's contained inside that?
Yeah.
Okay, thanks.
And so this is like a tremendously hard open problem. And it was recently resolved for T equals 3. It was a huge, big thing, and it was recently resolved in a monstrous paper for T equals 3. And that automatically gives us improved STP gaps for clustering. So any small improvement here automatically gives us something. So what do we know for the Johnson coverage problem so far? We know for T equals to 2, it's the vertex coverage problem, and that 0.9292 gap, it's not what we expect, but it's going up. And in our paper, we were able to look at layer 3. So all subsets of size 3, and we want to find vertices that hit it. And we showed that 7 over 8 is NP hard to approximate. And because of this, we also get some nice NP hardness results, which almost matches the UGC results that we had.
Karthik, when you say 3 hypergraph vertex coverage, it's like a sets of size 3, and you want to hit them with element of size 1.
Right.
Okay.
And the embedding almost goes through, because now you lose a bit more because it's 3 versus 1. So in the yes case, it's a distance 2, and in the no case, it's a distance 4. Instead of ratio 3, you get ratio 2. So the embedding is slightly worse. So what are the key takeaways? It's that we have improved in approximability of k-means and k-median in LP metrics. And now we use this transcript of this containment protocol to get this. And we also had to do this geometric embedding to go to other metrics. And the main question is if JCH is true. And I've been thinking about this with few people, and it looks like a tremendously hard problem. Sort of fits into problems that people think will require decades to solve. And so we're trying to write it up now, where we sort of see this in this larger framework that people have of proving tight results for CSP in approximability with perfect completeness. And this sort of fits into that framework. So at least it seems like it fits in a framework where other things are conjectured to be true. And so let me try to tell a few puzzles like open problems and some really hard open problems. Of course, JCH is probably the hardest open problem coming out of this talk. But let me try to give a few more puzzles that I think should be easily solvable, but somehow seem to elude. So if you look at k-means and the continuous version, so we have a tight understanding. I mean, we have some understanding for everything, but somehow the L infinity metric k-means sort of completely eludes me. I can't prove any hardness. I can't come up with an approximation algorithm that's significantly better. So when we say L infinity metric, so let me rephrase the problem. You're given n points in O of log n dimensional L infinity metrics and an integer k. And we want to find the optimal k clustering. K means clustering of this. You can pick centers wherever you are. And all hardness techniques sort of break. And at the same time, I can't come up with an approximation algorithm that's like, say, 1.5 approximation or something like that. So it's puzzling where the truth is for the continuous k-means in L infinity metric.
And what is a known positive result in L infinity metric?
9.
9. Okay.
Maybe not even 9. For k-means, it's 36, I think. So, and we know that if the dimension is n, then we have an inapproximability of 4. So yeah, but even then, when the dimension goes down to log n, there is no hardness or inapproximability. There's no hardness or approximability. So that's a very puzzling thing. And it really feels like a puzzle, not like a very serious problem. The other issue is when we embed into Euclidean metrics, we look at them as points, characteristic vectors, we're getting this 1 versus square root 3. And that's really annoying because you lose a lot of the gap that you get and you get weaker inapproximability results. And yes, one understands that things, even the approximation you can do better in Euclidean metrics, but is this really tight, like 1 versus square root 3, or can we get better embeddings? Maybe there is an embedding which gives 1 versus 2 instead of 1 versus 3. And so is there a better embedding of the Johnson graph in Euclidean metric? One direction that I have looked into in this is what if you put additional structure on top of already things that are there in the Johnson graph. And if you had, like, say, a Boolean hypercube structure, then you can improve this inapproximability from 1 versus square root 3 to, say, 1 versus square root 5. So that gives sort of hope, but then it makes it even worse because already Johnson coverage hypothesis, we don't know the truth. And now we are looking at special structures on top of that. So it makes it less plausible. So this is the other question on Euclidean metrics. And then let me just point out that for K-center, which is studied from the 80s, and for whose hardness of approximation does not require Pcp theorem or any of those things, it's just straightforward gadget reductions, we still don't know the tight answer in Euclidean metric. So if you look at the case where you are given candidate centers, we have square root 3 plus 1, that's like 2.73, and the hardness is square root 7, which is like 2.65. So there is a gap there. And if you look at the case where you can pick centers wherever you want, then we have 2 approximation, and we still don't know how to do better. And the hardness is at 1.82. So this is like a very simple, easy to state problem where there's a gap, and that the gap is there for like 50 years almost now. So this is for K-center. And as Saket was saying, there are these new versions that are coming up. And before that, let me say that K-min-sum, yesterday I said that we can show in general metrics. It's open to show anything in LP metrics. We can just rule out a p-task for now. There is this thing called capacitated clustering, which studied where you can't put as many points as you want into a cluster. So there's a capacity on how many points can be there in each cluster. And here, the best hardness results we know are the ones where for the uncapacitated version. So we don't know if putting a capacity makes it harder or not. So that's the open case here. And I guess this was recently studied in the FPT setting, where they were able to prove a highly non-trivial approximation result of 3. And before that, even constant was not known. So, and then there is this things called fair clustering, where you are given that, okay, you have some colored point set. Let's say you have colored it using C color classes. And you want that in each cluster, not only is your k-means objective minimized, but there's also a fairness constraint that you have, say, one of each color, or each color class is equally well represented, and so on and so forth. And then the question really is, does it make the problem additionally harder, or can you still solve it in the same time? From an approximation point of view, they say that, okay, if the uncolored or clustering version without any fairness constraint can be solved with approximation C, then adding the fairness constraint, whatever the notion of fairness, usually gives them C+2 or C+3 years, things like that. And then the question is that really needed? Can we prove hardness beyond what is known for fair clustering? or is fairness just an easy constraint that you can just accommodate approximation wise? Okay, so this is all the open problems. And thank you.
Thanks a lot, Karthik. So before anybody asks some open questions, let me, or other questions, I have a question now. Okay, so if I notice that if for a lot of these approximation, there was a paper in 19 by Cohen and other co-authors of him, where they showed that, like these gaps can be met in FPT world, like 1 plus, right? Now, can we have also on your Johnson's hypothesis some assumptions say that even in, say, if I take gap ETH or something, we can't do better than this? Like, is it?
So the problem is Johnson coverage is in FPT.
Sure, yeah, of course, parameterized by T, it is in FPT.
Right. And so we don't know anything from that point of view. And there is no reduction known from gap ETH with that structure.
Okay, so what do you mean by Johnson coverage is in FPT? When you say it means K plus T?
Johnson coverage is when T is some constant and you parameterize by K.
Correct. Okay, so then fine.
So then we know it's in.
No. Look at vertex cover, no?
Right.
Okay, so what are you asking? So if I'm asking you in some sense that can you cover at least T edges or something with K vertices, no?
Can you cover, right?
And that's,
can you?
So I give you a budget of K.
Right.
And I want you to cover as many edges as possible.
Right.
And that's W1 hard.
That's right. That's W1 hard, but there's a 1 plus epsilon approximation scheme.
Correct. I agree.
So that holds for Johnson coverage as well.
Sure.
And in general, it becomes harder to prove things because K means or K median in Euclidean metric, there is a 1 plus epsilon FPT approximation scheme.
I see. Okay.
And so you cannot expect to prove hardness results because eventually that will trickle down to here.
Sure. Okay. Thanks. Okay. So floor is open for everybody else. Please feel free to unmute yourself and ask questions to Karthik. Okay. So there is, I also know one more clustering constraint which people have studied, something called sum of radii, like, yeah, which I saw.
I saw it in Soda, I think, this year. There was some paper like that.
Yeah, so even before that, there was an old paper by, like, it came from some very good motivation. So the old, so there was a history of for long time, and they managed to get a very good set of approximation algorithm in like some 10-15 years back.
Mm-hmm.
But there also the capacitated version, it is not known in polytime whether it has a constant factor approximation. And we don't know even any constant factor approximation. So like whether there is an inapproximability of even constant is not known, but we also don't know any constant factor approximation.
Right. To me, the truth, all those places looks like there should be a constant factor. And yeah, so when I study a hardness problem, I make sure that I'm not trying to prove something that's false.
Correct. Sure. Okay.
Yeah.
So that's wonderful. Karthik, is anybody has question?
Yeah. So I was just asking, sir, is there any relationship between Turan number and the property B of the hypergraph?
The property what?
Property B of the hypergraph, that whether a K uniform hypergraph is two colorable or something. Minimum number of edges such that the K uniform hypergraph is two colorable or something like that.
Right.
Or is it the same problem or something?
I think you can formulate it to be the same problem.
So that is what I was saying. Then there are many results there for that, I guess, present for those numbers.
Right, but I think all of those results don't hold in generality, and the bounds particularly don't work. because there's a huge bound between lower bound and upper bound, and it's an
Yeah,
exponential gap.
Yeah, that's true. That's true. Yeah.
So the exponential gap is just too much to use any of those bounds.
Okay. Thank you.
Saket, I have a question for you actually. Do you know if there is any hardness of approximation result known for sum of radii?
Yes, I think for sum of radii, there is a constant factor approximation, and there is some hardness of approximation. Whether they are matching or not matching, I wouldn't know. So
I see. I think it should come out naturally, whatever the right answer from this JCH for that as well.
Yeah, so this is exactly why. So this is an exercise which I will try to do after your talk, just to understand what JCH is. JCH could do and explain.
Right. That will be great if more people. So there was a follow-up on JCH by Guruswamy and Sai Sandeep that appears in this Soda 22.
Okay.
Where they showed that if you look at the minimization variant, so clearly you can just do a T approximation for any of these problems. And they showed that unlike the hypergraph cases where T is tight, here you can go to T over 2. So they found an improved approximation algorithm.
For this, I see.
It still doesn't violate anything. It just says that this is you have to be more tricky to play hardness results here.
Here, I see. Just like unique game conjecture.
Yeah, just similar to that.
Yes. Okay, so if there is no question, it was very nice of you to Karthik to give us some insight into this completely new and amazing field of clustering. So thank you very much, and we will be in touch. So enjoy your time in India, and thanks a lot for agreeing to give 2 wonderful talks. It was, as always, amazing listening to you. Thank you very much.
Thank you, Saket, and the organizers for inviting me.